So welcome everyone to today's seminar, which is titled Making the Most Out of Noisy Quantum Computers, Strategies for Circuit Design and Error Mitigation. Our speaker today is Dr. Stefan Kuhn, who was awarded his PhD at the Max Planck Institute of Quantum Optics in Garching, Germany, in the theory division headed by Professor Ignacio Chirac. His PhD thesis was titled Quantum and Classical Simulation of High Energy Physics. Thereafter, he worked as a postdoctoral fellow at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, as part of the Tensor Networks Initiative. He's currently a postdoc in quantum computing at CASTC. Stefan, thanks very much for your presence today, and over to you.
Thank you very much for the introduction and the invitation and giving me the opportunity to present some of our recent work. And as Delia said, it's about making the most out of noisy quantum computers, namely strategies for circuit design and error mitigation. But before going actually to the core topic of the talk, I want to give you a brief motivation why we think that quantum computers might actually be interesting and it might be advantageous to use them. So there are a variety of applications where we think that quantum computers could be faster or more efficient than classical computers. So one of the things you probably heard about is Shor's famous factoring algorithm, which is concerned about factoring a large number into primes. And to the best of our knowledge, this algorithm would be exponentially faster than the best known classical algorithm. But there's also a variety of other problems where quantum computers are more efficient or could be more efficient. So, for example, combinatorial optimization problems, searching unstructured databases, for certain problems in machine learning, or also cryptography in general, because quantum states have just a very peculiar nature, and you can use this nature to actually design protocols that allow for secure communication. And since I'm a physicist, I'm mostly excited about this middle column here, namely quantum simulation. So basically, quantum computers allow us to simulate other quantum systems efficiently, which we cannot do classically. And there is a variety of applications you can think of, for example, in quantum chemistry, if you want to simulate molecules, or if you want to simulate out of equilibrium dynamics in particle physics, problems in cosmology, material science, and a plethora of other applications where quantum computers would be interesting. So we would all be very excited to have like a big quantum computer where we can solve all of these awesome problems. Unfortunately, we are not there yet. So currently we are at the verge of the so-called NISQ era. So NISQ is a term that was coined by John Preskill in this reference here and stands for Noisy Intermediate Scale Quantum. So what we have currently available is technology with on the order of 50 to 100 qubits. But these qubits are still suffering from a considerable amount of noise. So in particular, these devices are not large enough that you can do any quantum error correction to make them fault tolerant. So one kind of has to deal with the noise. And this limits, of course, the depth of the circuit you can faithfully execute on such a machine. And the first of these devices are even commercially available. So for example, IBM's Quantum Experience offers free access to small-scale quantum computers for everybody. And despite the limitation of these noisy intermediate-scale quantum computers, it has already been proven that such machines can outperform classical computers in certain tasks. So there was a famous example by a group around Google in this publication here where they demonstrated quantum supremacy or quantum advantage. So solving a problem on a quantum computer exponentially faster than on any classical computer. So what they used is this quantum computer here, Google's Sycamore chip with 53 qubits. And recently there has been a second demonstration of a quantum advantage using a photonic system in this reference. So despite the limitations of current devices, they're already kind of powerful and allow us to go beyond the capabilities of classical computers. But still, I mean, there are certain limitations. You suffer from all this noise and so on. So what I would like to discuss in the talk today is two strategies that might help to circumvent this problem to a certain extent, namely dimensional expressivity analysis, which is a tool for designing optimized quantum circuits for these small-scale devices, and measurement error mitigation. So a type of classical post-processing of the data after the final measurement on the quantum device, which allows to get rid of some of the errors. But before going into this, I was asked to give a little introduction. So I would like to start with a brief introduction to the circuit model of quantum computing before actually coming to the two topics that I promised to speak about. And then eventually I'm going to conclude with a short summary. So let's start with the circuit model of quantum computing. So the first thing we need is the quantum analog of classical bits. And it's basically just a two-dimensional quantum system. And in analogy to classical computing, we label the basis states of the Hilbert space with a 0 and 1, just like the states 0 and 1 of a classical bit. And you already see immediately that there's a decisive difference with respect to classical computing, namely the quantum mechanics allows for arbitrary superpositions of the basis states. So the most general single qubit state I can write down is given by this expression psi here, with some complex amplitudes alpha and beta. And I have to fulfill this constraint because my state should be normalized. And as you see, my qubit can actually be in a superposition of both basis states. So unlike a classical bit, it's not just in the 0 or the 1 state, it can actually be in a superposition of both basis states at the same time. Okay. What we ultimately want to do is at the end of our quantum computation, we want to extract information out of our qubits. So what we have to do is have some procedure of extracting information, and what we're using are measurements to do that. In particular, for all the talk, I'm considering projective measurements on the computational basis. And such a projective measurement collapses my state onto one of the basis states. So if I look at my example psi here, which is the superposition of the two states, it would collapse onto the basis state 0 with a probability given by the square modulus of alpha, and with a probability given by the square modulus of beta, it would be in the 1 state after measurement. So what I can do now is basically to get this information, I would just run my experiment many, many times, prepare the state, measure, prepare the state, measure, and so on and so forth. And then I can record this histogram of the basis states I've measured. So I would just get something like this. So the 0 state should occur with probability alpha square. If I just repeat the experiment often enough, and the 1 state should occur with a probability beta square. And you also see the difference with respect to classical system, because eventually the measurement changes my qubit state. So after I have measured it, it collapsed onto basis states, and I always will measure the same outcome. So that's very different from a classical system where you can like measure arbitrarily often and you do not change this. In general, we don't only want a single qubit because that would be very boring and we couldn't do much with it. So we want multiple qubits, and what we take is just like many copies of a single qubit. And then quantum mechanics tells us that the Hilbert space of the resulting system will just be the tensor product. And the most general state in the computational basis I can write down is given by this expression here with some complex amplitudes Ci. So this is interesting in particular because multi-qubit states can have a property that do not have any classical analog, namely they can be entangled. So what is entanglement? Actually, entanglement is something very complicated, and I just want to briefly scratch on the surface here and give you some basic idea. So for all, I would like to consider bipartite system, meaning composed of two subsystems A and B. So you could think of just having two qubits, or if you have multiple qubits, you divide them into groups A and B. So what is an entangled state now? Well, I will tell you what is not an entangled state, and everything else is called entangled. So a state that can be factored as a tensor product of its local constituents is called a product state or separable state. So whenever I can write my state psi as the tensor product of its constituents, it's a product state. Otherwise, the state is entangled. Of course, this is kind of an abstract definition, so let's do a little example here. So what you see here is a state psi1, which is just an equal weight superposition of all 4 possible 2-qubit basis states, 0, 0, 0, 1, 1, 0, and 1, 1. And despite the fact that it looks kind of complicated, it's actually just a product state because I can write it as the tensor product of 2 single qubit states, which are equal weight superpositions between 0 and 1 for each qubit. Okay. Another type of state could be this state, phi plus, which is actually an entangled state, because if you sit down and try to bring it into this format, you will see that there's no chance that you can write it as a tensor product of the individual constituents. And it's actually a very famous state. It's one of the 4 Bell states. So let's have a closer look at this Bell state here, which is given by this expression again. So it's just a 0, 0 plus a 1, 1. So it's a 2-qubit state. And you can imagine that I prepare the state in a lab or something, and then I separate the qubits arbitrarily far apart. So I could give 1 qubit to Alice and 1 qubit to Bob, and Alice and Bob are far separated, like a large distance. So what would happen now in this entangled state if Bob starts measuring his qubit? So from what we've just learned, if Bob measures his qubit, he would get the 0 outcome with probability 1/2, or the 1 outcome with probability 1/2. So basically for Bob, it just looks random. With 50%, he gets 0, with another 50%, he gets the 1 outcome. And since the measurement collapses the wave function, like the qubit of Bob, onto the basis states, the resulting wave function after measurement will look like this. So if Bob has measured a 0, the resulting wave function after measurement is just a 0, 0. And if Bob would have measured a 1, the resulting wave function is just a 1. So what happens now if Alice is applying a projective measurement after Bob has applied his measurement? Well, what we see immediately is that Alice measures with certainty the same outcome as Bob. So if Bob measured a 0, he collapsed the wave function into a 0, 0 state. And then if Alice measures her second qubit here, she would with certainty measure 0. And the same in the 1 case. So Alice would always measure the same thing as Bob, and the measurement outcomes are perfectly correlated. In particular, you see that the choice of measurement in one location seems to affect what happens on the other location, even if they are very far separated in space. So that's what people sometimes call a spooky action at a distance. And the reason is why these peculiar things happen is that the states of the qubits can just not be described independently. So the constituents, one of the constituents alone doesn't tell you the full picture about the entire state. You have to describe it as an entity. And this property, these type of peculiar correlations caused by entanglement don't have any classical analog. Okay, so that's a fundamental difference of a quantum computer, that you can actually generate these entangled states and use entanglement as some kind of resource for your computation. I have already said that we want to do computations, and to actually do computations, we have to manipulate our qubit somehow. And since quantum mechanics tells us that some state psi0 is undergoing unitary evolution in time under some possibly time-dependent Hamiltonian, we see that this expression here is just a unitary matrix that you apply to your state. So quantum gates are nothing but unitary matrices. And in practice, we want to restrict gates to non-trivially act on only a single or a few qubits, because anything else would be impractical. So if we have our chain of qubits here, then the unitary gate should just act, let's say, on a single qubit, 2 qubits, or 3. At least not on everything in the system at the same time. Just to give you some examples of quantum gates. So this table here shows some quantum gates. The first column is the name. The second column is the symbol, because I will show you this circuit notation in a minute. The middle column would be the matrix representation, and the interesting part is the last column, where you see how it acts on the basis states. So if you look at the first gate, which is called the Hadamard gate, you see that this is actually one gate that can take a basis state and put it into superposition. The X gate is nothing but the quantum analog of a NOT gate, so it takes the 0 state as an input and flips it, and the same with the 1 state. So this is just the quantum version of a NOT gate. The Y gate is very similar, but on top of that, it introduces phase factor, and the C gate is doing nothing as imposing a phase factor. But single qubit gates alone are not doing the trick, because I've just been talking about entanglement, and to create entanglement, you need at least a 2 qubit gate. In general, let's first discuss some more single qubit gates. So these gates are just a special case of more general single qubit gates, the so-called rotation gates, which are nothing but the exponential of the Pauli matrices x, y, and z times some parameter theta. And the reason why they are called rotation gate is because to every quantum state, you can associate a vector on the 3-dimensional real unit sphere, and applying these gates to a quantum state will rotate the corresponding vector on the unit sphere around one of the coordinate axes. So our z is taking this red vector here and would just rotate it around the z-axis. Our y would rotate it around the y-axis, and correspondingly, our x would rotate it around the x-axis with some angle theta. So, as I said, we also need 2 qubit gates, in particular if you want to create entanglement. And the most famous one is probably the C0 gate, which is nothing but a control NOT gate. So the first qubit here acts as the control. The second is the qubit, which is actually negated in case the control is 1. So basically, this gate does nothing if the first qubit is in state 0, and it flips the second qubit if and only if the first qubit is in state 1, as you can see here. First qubit is in state 1, second qubit gets flipped, and the other. Okay. And this is, of course, not the only 2 qubit gate. There are many more. Just to give you an example, there's the swap gate, which exchanges the state of 2 qubits. You can also go to a larger number of qubits, can be 3 qubits. Then you would get a CC0 gate, which is called the Toffoli gate. So there's a plethora of quantum gates you can think of, and you can use in your computation to manipulate qubits. So what do we see from that? If you're familiar with classical computing, you know that the classical version of this Toffoli gate is basically sufficient to represent any Boolean function. It can always be expressed in these Toffoli gates. So this immediately tells us that a quantum computer can also do all computations a classical computer can do. So you can implement any classical computation on a quantum computer and replicate classical computation. And as I've already mentioned, in particular, the Hadamard gate allows you to create superpositions of basis states. So if you take the 0 as an input, you end up with a superposition between 0 and 1. And the C0 gate is crucially important for creating entanglement. So basically, if you use the appropriate product state as an input, the C0 gate is able to create something that is not a product state, meaning that you have an entanglement. And since quantum mechanics is linear, you cannot just apply gates to basis states, but you can apply them to arbitrary superpositions of basis states. So for example, if I take again the most general 2 qubit states being a superposition of all 4 basis states, you can directly apply the C0 gate on all of them. And you see the first 2 terms in the superposition stay untouched, whereas in the second two terms, the second qubit is flipped because the first qubit, which is the control, is a 1. And then you can basically do the same you do in classical computing. You can string these operations together and build up circuits, so-called quantum circuits. So you have to read this diagram from the left to the right. The initial states here indicate the starting states of the qubits, which is typically all zeros, but any product state would be fine. And then along this time direction here, you apply various gates on your qubits, eventually manipulate them to obtain some resulting state here. So the depth of a quantum circuit is nothing but the maximum length of a directed path from the input to the output. So in this example, the depth would be 4. And eventually, as I said, we want to get some information out of our quantum computer. So at the end, you have to measure the qubits or a subset of the qubits to obtain some information about the state you've prepared here. And this measurement is indicated by this box with a little meter inside, and the double line indicates that after measurement, one basically obtains classical. Okay, so the question is, one can of course think about this, but I want to give you some intuition why this could be more powerful than a conventional computer. So the first thing you immediately realize is that if you have n qubits, the resulting Hilbert space is the tensor product of the single qubit Hilbert spaces. So in particular, the dimension of this Hilbert space for n qubits is 2 to the power of n. So you have an exponential number of basis states to encode information. And in particular, if you think of something relatively modest like n equal 100, so 100 qubits, you can already encode more information than any classical computer on the Earth. So there's really a large amount of information you can store in a quantum system compared to any classical. The second thing is, I've already mentioned that a couple of times, that you can build superpositions of your states. So your qubit can be in a superposition between the 0 and 1 state, and that you can send the superposition through the quantum gate and apply it to each constituent of this state of the superposition in basically one operation. So if I send this superposition state through here, I can apply my unitary U on both states at the same time. That's sometimes referred to as quantum parallelism. And the final thing is that multiple qubits can be entangled, as I've shown you in this example. So you can create correlations between them that have no classical analog. And these are 3 of the main ingredients which make quantum computing actually more powerful than classical computing. Okay. So let's do a simple example here. Let's look at the Bell state we have already seen before, and the circuit that prepares that Bell state. And it's actually a very simple circuit. So it's just a Hadamard gate and a CNOT gate, and eventually we can measure it at the very end. So what happens if I apply the Hadamard gate? Well, I apply it on the first qubit, so I will put it in a superposition between the 2 basis states, and I can just rewrite it in the second line here in this manner. So it will be a superposition of 2 basis states. Then I can apply my CNOT gate, which is doing nothing to the first term, because my first qubit here, which is the control, is 0 in the first term, but it will flip the second qubit of the second term. So you see, indeed, this is the phi plus Bell state we had previously. And we have generated an entangled state on our quantum computer. And eventually we can measure it. So from the state C, that in 50% of all times we should measure a 0-0 outcome, and in 50% of all time we should measure 1-1 outcome. So what I can do now is I can actually implement this on a quantum computer. So I used IBM QWiGo for this experiment here. And you see what you get from the quantum computer. So this histogram of the basis states is more or less what one would expect. So I got 50%, 51% of all time 0-0 state, and 43% of all time 1-1 state. In case you're wondering why there are some other states present in this histogram, that's exactly due to noise. So you see that even such a very simple circuit has non-negligible effects of noise, and these lead to some contamination of different basis states. Okay. So where do we basically stand? Well, we have these small or intermediate scale devices. But as I have shown you in this little example here, they still suffer from a considerable amount of noise. So you cannot actually execute huge circuits on those machines faithfully because eventually noise will take over. At the same time, even such a limited small scale quantum computer with 50 qubits and a non-negligible amount of noise is already powerful enough to demonstrate quantum advantage, meaning solving a problem that you cannot solve on a classical computer. On the other hand, if you think about quantum algorithms for solving quote unquote useful problems, for example, thinking of Shor's factoring algorithm, you would need a large number of qubits to run such an algorithm. The circuits are typically kind of deep, at least a lot deeper than what we can do on current existing quantum hardware. And probably you need full quantum error correction to actually run such a circuit. So far, what we can do are only proof of principle demonstrations, and current quantum hardware is not yet sufficient to actually run these complicated algorithms. So the question is actually, how can we utilize existing quantum hardware in a beneficial way? And one field of active research is hybrid quantum classical algorithms, which seem to be the most promising candidates. And the idea here is that you actually combine the quantum device with a classical computer, because after all, our classical computers are still very powerful. So the idea is that the quantum device serves as a kind of co-processor, which we use to tackle classically hard or intractable parts of the problem. Then we measure some information on the quantum device and feed it back into our classical computer and process it there with conventional classical computing methods. And this way, basically, we can do something useful and gain some advantages, just having very modest quantum hardware with, say, order of 30 something qubits, and we don't have to run these super complicated quantum circuits and so on. So in particular, in the context of physics, this problem or this concept has been studied a lot and is kind of popular because you can actually use it to find the ground state of a quantum Hamiltonian, which is a very common problem which we encounter a lot in physics. And how do you do that? Well, you define a cost function, C of theta, which is nothing but the energy expectation value of the Hamiltonian in some ansatz state psi of theta. So your ansatz depends on some real parameters. And how does now the quantum device come into play here? So the way you choose your ansatz is you run a parametric quantum circuit on such a device. So the psi of theta, for example, could look like this, that you have a bunch of rotation gates, which depend on some angles, theta 1 to theta 8 in this example. And in the middle, there's a layers of C naught to have a circuit that is able to generate entanglement. And then eventually we measure the value of the cost function on the quantum device and give it back to our classical computer. And provided our ansatz we have chosen here is expressive enough, the minimum of the cost function should actually be the ground state energy of the Hamiltonian, and the corresponding state is the ground state. So how do we do this minimization? Well, we just run a feedback loop between the classical computer and the quantum device. So we initialize it with some parameters, measure the cost function for this parameter set, give it to our classical computer, and then use some classical optimization algorithm to minimize the cost function based on the outcome from the quantum device. So you could just think of running a conjugate gradient or something more elaborate. So you just iterate this feedback loop many, many times, and then the hope is that you start with some value of the cost function, and as you continue the iterations, that the cost function value you have is actually decreasing and hopefully converging to some value, which would then be your ground state energy. So what are the advantages of such an ansatz? First of all, it's very flexible. You can think of like pretty much any ansatz design you want. Like you can change the rotations, the type of the structure of the rotation layers. You can use different entangling layers and so on. So in particular, you could tailor it to the quantum device you have. It might be easier to realize a certain type of gates than the others, so you can just use those in the ansatz. You don't have to actually implement a very complicated Hamiltonian. The only place where your Hamiltonian plays a role is in the final measurement when you measure the value of the cost function. So you don't have to generate the interactions of your Hamiltonian on the quantum device. And this setup is partially resilient to at least systematic errors. So for example, typically gate operations on a quantum computer are not perfect. So they might over-rotate always a little. Instead of an angle θ1, they go at angle θ1 plus some epsilon. And since you're just trying to find a set of angles that minimizes the cost function, this minimization process will just even out this systematic bias if one gate is constantly over-rotated. At the other hand, it also has some challenges because you have great flexibility in the design of the ansatz, but then the question arises, what is actually a good ansatz? So how do I choose an ansatz that is sufficiently expressive for the type of problem I want to solve? And one thing I also want to avoid is to have redundant parameters in my ansatz, because I showed you this little example with just a few gates, and you saw that there was already a considerable amount of noise. So if I have gates in my ansatz that do not contribute to the states my ansatz can represent, I'm just introducing noise for pretty much nothing. So I don't want to have any redundant parameters in such an ansatz. And despite careful ansatz design, there will still be a considerable amount of noise in the quantum device. So one question is, how can one deal with this type of noise? And in particular, these are the questions I want to address throughout the rest of the talk. But before going into dimensional expressivity analysis and measurement error mitigations, are there any questions up to here? Okay, this does not seem to be the case. Then I will just continue. Okay, so the first thing I want to talk about is dimensional expressivity analysis. And dimensional expressivity analysis is essentially tailored towards answering the first two of these questions, like how to choose an expressive ansatz and how to avoid redundant parameters. So how should you actually choose such an ansatz? And there are various competing, let's say, interests here to choose a good ansatz. On the one hand, you want to put a lot of parameters, parametric gates in your ansatz, because with every parametric gate you add to the ansatz, the space of the states you can represent is just growing. So the larger you make it, the larger your solution space might be, and the more likely it is that the solution is actually reachable. At least adding more gates doesn't decrease the expressivity. So from that point of view, having a lot of gates doesn't work. You also want to add a large number of gates to not introduce artificial local optima. So that's kind of a technical point. But as I said, we are running a classical optimization algorithm. And if you have some kind of parameterization that separates states that were originally close in state space to two parameter configurations that are far apart, that might actually introduce artificial local optima in which the optimizer can get stuck. On the other hand, you want it to be small to reduce effects of noise, because every gate operation will come with a certain level of noise. And it should also be small because running a high-dimensional classical minimization problem is actually non-trivial, and these optimizers work best the smaller the number of parameters. So for the rest of the talk, consider an optimal circuit for this variation quantum eigensolver to be maximally expressive. So it should be able to generate all physically relevant states. And at the same time, it should be minimal, meaning there should be no unnecessary gate operations, parametric gate operations in my ansatz, which do not contribute to the space of reachable states. And what dimensional expressivity analysis is actually is a mathematical framework allowing us to determine if a circuit is both minimal and maximally expressive. So how does this work? Well, let's start with a simple example. So I have a parametric quantum circuit here composed of rotation gates and a C0 gate. So what this parametric quantum circuit is doing is taking a bunch of real parameters that are chosen from some kind of subspace of r to the power n and generates some state c of theta. So from a mathematical point of view, I can interpret this parametric quantum circuit as a map taking a real input vector and mapping it to the complex state space phi of theta. So in particular, I have my parameter space P, which for all practical purposes is a real manifold. And my circuit manifold, so the circuit manifold is nothing but the image of this map C. And the question we basically want to ask are, which of these parameters here are necessary to generate the circuit manifold? So you could imagine a situation there you can actually get rid of 1, 2, or maybe even more of those parameters, and you would still perfectly generate the same circuit manifold. So in that sense, you found a redundant gate because it doesn't contribute to the circuit manifold. So how do we do this? Well, basically we just use a simple geometric picture looking at the tangent space of our circuit manifold. So if this white object here is the tangent is the circuit manifold, then we pick a point and locally check the tangent space, which is indicated by this red plane here. And this tangent space is spanned by the tangent vectors, which are nothing but the derivative of my states with respect to the individual parameter. And then checking for a redundant parameter is relatively simple. All one has to do is to check if the tangent vector corresponding to the parameter is a linear combination of the previous tangent vectors. So in this example, I would have the blue and the green tangent vectors, which are enough to span the plane. And then if I would start adding another parameter, which corresponds to this dashed yellow arrow here, this would be redundant because I can perfectly express this yellow arrow as a linear combination of the other two. So basically, this already gives us an algorithm how to identify redundant parameters given a circuit design. So we just iteratively check, starting from theta 1, if the subsequent parameters are redundant. And for all practical purposes, we can always assume that theta 1 is never redundant, because as long as you choose a non-trivial parametric gate, this will actually have an effect. So basically, all we have to do is to check if the tangent vector for the parameter k plus 1 we are about to add is a linear combination of the previous tangent vectors. And then we can remove redundant parameters. So just a technical thing here, removing the parameter means actually setting it to constant value. But since we're mainly concerned about rotation gates, which are of this form here, we can always choose the parameter to be 0, and then we have actually an identity. So we really remove it. But if you think of something mathematically more abstract, there might be a case where you just set the parameter to constant value. Okay, so how do you do this in practice? As I said, theta 1 would never be redundant because the parametric gate we have at the beginning is always non-trivial, or it's something you can easily check by hand, so it's not complicated. And then for any additional parameter, theta k from 2 to the 2 to n, we repeat the following step. We construct the real Jacobian. So why the real Jacobian? Well, our parameter space is a real manifold, as I've said at the beginning. So you have to consider a linear combination with real coefficients in your tangent space. So all we do is we take our state vectors and just split real and imaginary part and write them on top of each other. And this real Jacobian contains nothing but the tangent vectors. So basically, to check now if the parameter k we've just added is redundant, all I have to do is check the rank of this matrix. Because if the new parameter I added will be redundant, it's a linear combination of the previous columns, and therefore the rank of the matrix would not be full. And just for a technical point of view, I can, instead of checking the Jacobian JK for full rank, I can also check this matrix SK, which is just the transpose of the Jacobian times the original Jacobian. So that doesn't change the rank. Okay, so it sounds like we have a practical recipe given a circuit layout that we can follow and actually determine if there are any redundant parameters and if it's maximally expressive. But if you pay close attention, you will already have realized that this is not very useful in the form I've just shown it you, because the memory requirements in a classical computer are actually exponential in the number of qubits, just because I have the state, the tangent vectors here in my Jacobian. So they grow exponentially with the size of the qubits. So the question is, has this any practical use? And the answer is yes. We can basically use the quantum device to efficiently measure our Jacobian or the matrix SK. So the idea is very simple of this, similar to this hybrid quantum classical setup, that we feed the quantum device with a bunch of parameters and get back the SK matrix from the device. So how does this work? Well, there's a bit of technicality involved here. So basically, one thing you have to realize is if you sit down and do the calculation, that you can recursively construct these SK matrices from the previous SK matrix and then just a vector whose entries is the real part of the overlap of the tangent vectors. So once we have the previous SK matrix, we know how to construct the next one if we can obtain this vector. And the first one is always 1/4 for all the cases we consider. So the key ingredient we need here is that for the type of gates we are considering, namely the exponential of some matrix G, where G is itself a gate. If you think of the rotation gates Rx, Ry, or Z, the derivative is essentially again a valid quantum circuit. So what do you mean by this? The state Rg corresponding to, let's say, some initial state, and you apply the gate to it, then the tangent vector or the derivative with respect to theta is again a circuit up to this complex factor 2i. So why is this now interesting? Well, basically it means I can prepare the states here on my quantum device. And actually now if you find an algorithm to measure the real part of the overlap of two states, we are in business. We can just measure these overlap terms on the quantum device, construct this vector AK. From the vector AK, we get the matrices SK, and then we use a classical computer to check the rank of the K times K matrix. And it turns out that this is indeed possible. I don't really want to go into the details here. So it was shown in these two papers how to do this. So I just want to show you a very simple example. So take this simple circuit with two rotations only, Rx, Rz. Now, if we want to check if the second parameter is redundant, we would have to compute the real part of this overlap, and the circuit for doing this is given here. So what we have to do is introduce an ancilla qubit, and then basically on top, you see the original circuit up to two additional gates that are coming from the derivatives, as I've shown before. And they are connected to the ancilla via a controlled operation here. And there's like you put your ancilla initially in a superposition, and then eventually you undo the Hadamard gate and you measure the ancilla. Why? Well, the probability of the ancilla being in state 0 is actually proportional to this real part of the overlap. So basically all you have to do is modify the original circuit a little bit, add an ancillary qubit to it, measure the probability for the ancilla being in 0, and this gives us the real parts of the overlaps, and this way we can actually construct these matrices. So this was a lot of theory, but just to show you that this actually works in practice, here are some results. So we actually checked an example on actual quantum hardware given by this circuit here. So we apply 4 rotation gates, first a Z, then an X, then a Z, then a Y rotation gate. And it's fairly easy to see that the number of independent parameters is just 3. And actually the 4th rotation gate is redundant, so it's not generating anything physically useful. So what we have done here is we actually checked this on quantum hardware. So let's focus on the panel A for a second. So the x-axis is indicating the k, so the number of the parameter we're adding. And since the first one is always non-trivial, I start with k equals 2, 3, and 4 here. And what you see here is the filled symbols correspond to the exact solution, where the triangles are the smallest eigenvalue of the matrix Sk, and the dots are the second smallest eigenvalue, or correspond to the second smallest eigenvalue of the matrix Sk. And as you see, if we encounter parameter 4, we actually have a 0 eigenvalue of the matrix Sk, meaning it's not full rank anymore, and that this parameter 4 is actually redundant. So the open markers here you see were obtained from an actual quantum device, so in that case IBM Q Orense, and you actually see that it agrees fairly well with the exact data. So the different colors of the markers just corresponds to a different number of measurements taken at the end, ranging from 1,000 over 4,000 to 8,000. But you again see it's not perfect, right? Like quantum devices have some noise, so you don't encounter perfect 0, but you get a pretty good idea that parameter 4 is actually redundant. And looking at the other panels, we've just tried different quantum devices. So this was the IBM Q Orense chip. We also ran it on Santiago, Valencia, and Vigo. And you see that the performance is pretty much similar on all of them. And in all cases, we kind of identify the force parameters from that. Okay. Just to show you a more complicated example, so one doesn't have to do it for just a single qubit. The same thing here is done for this more complicated circuit, where this parameter R8 is redundant. And again, you see that, okay, the quantum device is kind of giving results that are compatible with the analytical one. Of course, the circuit is much larger and a lot more complicated. So in certain cases, the results are more quite a bit off. But overall, if you would just run it a couple of times, you see that around parameter 8, one would get a good indication that RZ with P8 is actually redundant. So just to sum it up for dimensional expressivity analysis, it's a framework which allows you to optimize a given circuit structure and to identify redundant parameters. Can also do some other things I have not been talking about, like remove unwanted symmetries. And basically the key ingredient to do this in practice is to use a hybrid quantum classical approach, which allows you to perform this algorithm efficiently. Okay, so before moving on, are there any questions up to here? Okay, that does not seem to be the case, then I will just proceed. So the last part of the talk, I want to briefly talk about measurement error mitigation. And as you have seen previously, right, like current quantum devices are very noisy. So if you remember that's Bell state example, the hardware results were quite a bit different than the ideal results. And I mean, the reason is for that is that you have all kinds of sources of noise. For example, your gates are not perfect. And even if you apply a gate on the first qubit, there will always be some crosstalk to the second qubit. The device couples to the environment, and the measurement process / readout itself is kind of noisy itself. And if you look at error rates, you see that the measurement / readout process is among the most error-prone operations on current noisy intermediate scale quantum devices, with error rates ranging a couple of 10% in the worst case. And what is error mitigation now? Well, error mitigation generally sums up techniques for trying to compensate some of these errors. So if you want to know more about the more general framework here, there's a nice review paper here. But for all what follows, I would just like to focus on readout errors, because as you can see, readout errors are the most dominant sources of errors in current devices. So what we want to do here is to develop a simple, low overhead, resource efficient mitigation scheme that is suitable for small devices, but can also be applied to larger devices. So for all that follows, I want to make a few assumptions, namely that measurement errors are the only errors on the device. I don't consider anything else. That measurement errors arise from bit flips, meaning erroneously recording a 0 as a 1 and vice versa, and that these readout errors are uncorrelated between different qubits, and that these bit flips occur with a constant probability for each qubit. And the basic idea to do this mitigation is to construct random operators O tilde such that the expectation value subject to noise one obtains from the device coincides with the true expectation value. So the expectation value of O tilde measured on the noisy quantum device, which is indicated by this E here, should be equal to the expectation value we actually want to measure. So this is what we're trying to do. And I'm not going into the technical details here. I just would like to give you an idea how this works by considering a simple single qubit example. So basically, we consider a single qubit and we consider an erroneous readout. So with probability 0, we will actually record a 0 as a 1. And similarly, with probability P1, we accidentally record a 1 as a 0. And what we want to measure as an observable on this qubit is just the Z operator, so which is this matrix. So what can happen now? It can happen that I have both outcomes correctly recorded on my device. So this would happen with the probability 1 minus P0 times 1 minus P1. And this would correspond to actually measuring the operator I want to measure. It could happen that I record both cases incorrect. So basically, I just exchange the basis states. This would happen with probability P0 times P1. And this would just correspond to measuring the negative of Z. Similarly, it could be that just outcome 0 is recorded incorrectly. So basically, this would mean I always get the 1 state, and the 1 state has a -1 eigenvalue. So my effective noisy operator would be a -1. And similarly, the 1 outcome could be recorded incorrectly. So the 1 is flipping and going to 0. In that case, my noisy operator would be just the identity. So now from this table, going through all of this consideration, I can construct the expected value of the noisy operator, which is just given by the probability times the actual operator I measure. And simplifying it, I get a very simple expression. So let's have a look at this expression here and see what we can do. So what I can basically do now is take the expectation value of this expression in some wave function psi, and then invert the equation. So I solve it for the true expectation value I actually want to have, which can be done, and then it just looks like this. So why is this now useful? Well, if I can construct the operator C tilde, if I know what it is, I can basically measure this on the quantum device. So from my noisy quantum device, I can obtain this quantity. And provided I have the flip probabilities of the qubits, I have on the right-hand side now something that allows me to compute the true expectation value I actually want. And the flip probabilities can in fact be obtained very simple from the quantum device. Since we assume that they are all independent, all we have to do is run 2 additional circuits for each qubit before we do our computation. So we just run an empty circuit and record how many 1 outcome it produces, because the 0 state should be untouched, which gives us the flip probability P0 for qubit Q. And similar for P1, we do the same thing, but we add a single X gate, which generates a 1 state initially, and then we measure the number of 1 outcomes. Okay. So with this very simple calibration procedure, one basically has all the ingredients to reconstruct the true expectation value from the noisy measurement. And okay, I've shown you a very simple example. So just to show you that this derivation can be generalized, then it gets a bit mathematically involved. But basically what we have here is a formula for arbitrary observables in the computational basis, and they can be expressed as a linear combination of the noise-free operators, with these gamma factors being nothing but the flip probabilities of the qubit. So basically what we get is a set of equations, and if this set of equations can be inverted, which is actually possible as long as the sum of the flip probabilities doesn't exceed is not equal to 1. Then one can start reconstructing exact expectation values from noisy measurement outcomes and the flip probabilities of the qubit. So just to show you that this works in practice, here's an example showing data obtained for various number of measurements at the end and 1050 repetitions of taking random wave functions. And what we looked at is the absolute error between the exact and the mitigated and the unmitigated results. So what you see is the mean value of this error and the standard deviation in blue of this error for the unmitigated results, which are open markers here, and the mitigated results. And you can actually see that while the unmitigated data saturates quickly at some kind of error level, you can basically bring it down to a polynomial in the number of measurements at the end again, which is actually what we expect from the ideal case. So if you're familiar with this measurement process, the ideal case should scale as a power law s to the power of minus 0.5. And if we fit our data here, which we got from a classical simulation, so we just simulate a quantum computer with readout errors classically, it goes basically perfectly back to the case. So this is, of course, like a check that everything is working, and then we go back to the power law decay. But the real proof, the real benchmark basically is trying it again on quantum hardware, which we did in a second step. So what you see here is basically the same data, but now using actual quantum hardware, namely the IBM Q London chip. And again, you see the unmitigated results for the absolute value of the error here and the standard deviation of this error value here. And you see again, like in practice, if you don't do any mitigation, basically the precision you can reach tails off fairly quickly, and there's not really a point of taking more measurements. On the other hand, if you apply the same error mitigation procedure I've shown you, you can basically improve results from here to here by roughly 1 order of magnitude. And if you do the same power law fit, we see that we're not exactly recovering 1/2 again. In particular, if we fit through all the data points, which is the purple line. And this is because we've neglected the other sources of error. And eventually, if we got rid of the most dominant source of error here, we feel the effect of other sources of noise. So that's why it eventually also starts to tail off, but the value of precision we are able to obtain is much better than not doing it. Okay. So just to sum that part up, what I've shown you is a low overhead cost error mitigation method, which actually is only a polynomial and overhead for local Hamiltonians, which is what we typically care about in physics. And I've just scratched the surface here, so you can also do a probabilistic version of this mitigation scheme, which we're currently kind of working on. This idea of constructing random operators is in fact very general and can potentially be applied to a lot of other errors. For example, we could try to address relaxation errors, which is related to the finite lifetime of the qubit. We could also incorporate correlations between the qubits. So at the beginning, I said we neglect them for simplicity, but it should be possible to include a certain amount of correlation as well. And there are many other things you could think of doing with this very general scheme. So this is where I would basically like to stop. I have shown you and hopefully convinced you that we have this noisy intermediate scale quantum devices. And what we hope to use them for, at least from a physics point of view, is for the upcoming years, possibly hybrid quantum classical algorithms, because they leverage on the advantages of both worlds, kind of. And I've shown you 2 methods which are tailored towards applications on these devices, namely dimensional expressivity analysis, which kind of allows you to design a minimally, maximally expressive circuits for such setups, and a measurement error mitigation scheme, which allows them to tackle the most dominating errors on such devices. And I mean, just to give you an outlook here, so far dimensional expressivity analysis can only tell you if you're maximally expressive or not, but it doesn't allow you to quantify the approximation error of a given ansatz a priori. So that's something we're actually working on. Then, as I said, this random operator construction is very general, and we think it can be extended to other types of errors. So we're actually also working on this. And I mean, after our quantum hardware is progressing relatively quickly, so while the simulations have shown you were on rather small scale devices, we hope that we can actually extend and scale up to larger system sizes in the future. So with this, I would like to leave it, and thank you for your attention.
Thank you, Stefan, for your presentation. If anyone has any questions for Stefan, please raise your hands or unmute and ask your question. So I will ask a question. I think it was, sorry?
Sorry, I cannot see raised hands, so if anybody has a question, please.
I will ask a question then. So I think it was in your previous slide, you said that they will use, hybrid quantum classical algorithms are promising for these devices. So how will this be imagined as a system? Will it be a normal, will it be a regular supercomputing system that we have nowadays with a quantum booster that we can send part of our jobs to?
You can think of these. I mean, current devices are still a little bit small that you probably don't need a supercomputer to interface it to do this minimization. But once it exceeds a certain system size, that's definitely a way to think about it. That it would be some kind of accelerator, let's say.
Yeah. And this depends on materials, yeah, mostly? Or for the quantum, you said quantum hardware is advancing quickly. That's due to materials that decrease the errors?
Yes, so this is one big thing that people are constantly trying to decrease the error rates. And also one limitation is like connectivity. So if you look at the architecture of current devices, they are often something like a line or so on. So that means not every qubit can easily talk to its neighbors. So there are also some improvements on getting better connectivity. And I mean, in general, I would say it's still an open question, which is the best architecture. So superconducting qubits so far seem to be the most developed ones, but trapped ions are, from a physicist point of view, actually a very nice system because it's a very clean system. You only have very few degrees of freedom. You understand them very well. They can be controlled very well in the lab. But trapped ion technology is it's advancing, but it's the largest quantum computers available so far are all with superconducting circuits. So I think it remains to be seen what will be the winning technology.
Okay, thank you. Ferenc, you have a question.
Yeah, thank you very much for the nice talk. I just have one maybe silly question. Does it depend the kind of susceptibility for errors on the type of state, on the type of states you have? For example, if you have a completely entangled state, then that is more susceptible to errors than if you have a pure state, or?
That's actually a good question. So it depends a bit on the point of view you take. So a product state is in general simpler to create than an entangled state because any product state can be generated by just local operations. So yeah, if I take, for example, this picture here, so starting from a 0, 2 rotation gates in a row, an RY and an RZ, let's say, without any entangling operation is enough to generate arbitrary 4-qubit product states. So you need a lot less gates to generate them. So from that point of view, I think you will have less errors because less gate operations. And 2-qubit gates are typically 1 order of magnitude more erroneous than single-qubit gates. So if you can get rid of the CNOT gates, you kind of save some erroneous operations. From that point of view, yes, I would agree.
Mm-hmm. Thank you.
Then, in general, I'm not sure if you can say entangled states are more error-prone to external perturbation than product states.
Thank you.
Okay, does anyone else have any questions, other questions for Stefan? I will take that as a no, in which case I would like to thank Stefan very much for his presentation for our seminar today. Our next seminar is next Tuesday. Our speakers will be Jakob and Simone, and they will talk about, I believe, the PRAISE project, which is linear algebra, Krylov subspace methods, and multi-grid solvers for the discovery of new physics. So you hope to see you then. And again, I would like to thank Stefan for being our speaker today. Thank you very much, and bye-bye, everyone.
Thank you very much. Thank you, Stefan.